Thanks, David. So good afternoon, everyone. My name is Gautam Sabnis. I'm a computational scientist in Dr. Vivek Kumar's lab. I'm a statistician by training. In today's talk, I want to present some very preliminary but encouraging results for a machine vision based frailty index for diversity-outbred mice. So this is the overview of the talk. I'll start by talking very briefly about frailty index and motivate why we develop machine vision based approach to calculate frailty index. I will talk I'll talk briefly about how we apply computer vision tools to extract features from videos of open field assays in mice. And finally, I'll apply all this to predicting the frailty and other things of a mouse using the video features. So aging is a terminal process that affects all biological systems. Biological aging, however, in contrast to chronological aging, occurs at different rates for different individuals, i.e. it's heterogeneous. So the concept of frailty is used to quantify this heterogeneity in biological aging. Frailty index, FI, is used to quantify this heterogeneity, and frailty index is the most commonly used tool for quantifying frailty. In the mouse frailty index, a trained individual scores a mouse on a set of age-related health deficits. The presence and severity of each health deficit is scored as 0 for not present, 0.5 for partially present, or 1 for present. For example, gait disorders is one of the health deficits. So a mouse is scored 0 if it has no gait disorders, 0.5 if it has mild disorders, and 1 if it has severe gait disorders. Another example is kyphosis, which examines the curvature of the spine. And there are other deficits that the mouse is scored on. Finally, these items are aggregated to produce a cumulative score. And this cumulative score is defined as the frailty index. Frailty index has been shown to have several benefits. They have been successfully used to evaluate various aging interventions and construct chronological age and mortality models. Also, but they also have certain limitations. So frailty scoring is labor intensive and it is challenging. There is also scorer-based variability and poor inter-scorer reproducibility. For instance, we conducted a study with black 6 mice, where each mouse was scored by 4 different trained experts, and they assigned a manual frailty score. Here, the manual frailty score has been normalized, so it lies between 0 and 0.5, or more generally between 0 and 1. And inspection of data showed a scorer effect of the manual frailty index score. For instance, scorers 1 and 2 tended to generate low and high frailty scores, respectively, compared to the average. We fit a linear mixed model and found 42% of the variability in the manual frailty score was due to a scorer effect. So although the frailty index is an extremely useful tool for aging research, an increase in its scalability, reliability, and reproducibility through automation would enhance its utility. We address this by producing a scalable automated visual frailty index using video-generated features. We used machine vision-based techniques to extract an array of features, many of which show strong correlations with aging and frailty. We generated one of the largest frailty data sets of the mouse with an associated open field video data. And then we trained machine learning models to accurately predict age and frailty from video features. However, we did this only in the isogenic mouse strain Black 6Js. So we want to extend this to more genetically diverse populations, the DO population, for improved translatability. So how do we go about quantifying morphological, postural, and behavioral features from video? We start with an hour-long top-down video of a freely moving mouse in the open field. The open field video is processed by a tracking network and a segmentation network to produce an ellipse fit of the mouse per frame of the video. We use the fitted ellipse to extract morphometric features, such as the length and the width of the mouse. We also extract engineered features, like how much a mouse can bend the spinal flexibility. It's quite well known that changes in gait are a hallmark of aging in humans as well as mice. The prevalence of gait disorders and irregularities increases with age. We have established methods to extract pose and gait from freely moving mice in the open field. Uh, uh, we extract, more specifically, we extract pose using a pose estimation network. What this network does is it produces a 12 two-dimensional key points for each frame of the video, describing the pose of the mouse at each time point. And each stride the mouse makes is then analyzed for its spatial, temporal, and postural measures to extract gait measurements. For example, step length, step width, and stride length. We also extract whole body, like the lateral displacement of tail, the nose. All these features, as we will see, prove to be useful for predicting different like frailty index and age and etc. and so on. So we already have data on the black 6 mice. We have published on this. We have roughly 530 mice. We piggyback on an existing diet study that is being conducted by Dr. Gary Churchill's lab, and we collect data on 300 DO mice. So the mean FI score, which is shown on the FI score, which is the cumulative FI, which is shown on the y-axis, increases with age, which is shown on the x-axis. We can see to this piecewise linear regression model that has been fed to the data. But you'll see that there's an observed heterogeneity in biological age among mice within the same cohort. For example, this mice, which is greater than 200 weeks old and has a frailty index of 13, close to 13. There's another mouse which is 200 weeks old, but has a frailty index less than 3. And then there's a mouse that is close to 100 weeks old, but has roughly the same frailty as a mouse that is 200 weeks old from here. So although we may not be able to appreciate the differences in these 30 seconds clips, our networks that we train are able to extract idiosyncratic differences amongst these videos from these mice.
Tom, can you hear me? So yes. What is 1D, 2D, 4D, 20? I assume those are different.
Right. Yeah, sorry, I forgot to mention this. So these are the diets. These are ad libitum diet, the regular diet. This is 20% of the entire diet, 40% of the entire diet. And then this is 1 day fasting and 2 day fasting, like different diet regimes.
So 20% fat and 40% fat. I think this is high fat, high sugar diet, the 20 and the 40. And then the 1 day and 2 day caloric restriction.
Okay, so we have our features and we have these manual frailty scores scored by the experts. You can go ahead and model the frailty scores and the features and build a predictive model. So the features look like this, as I described. There are certain covariates, there are gait measurements that we get from the pose estimation network, morphological measurements, behavioral measurements, where an annotator goes in and annotates the frames which contain this behavior. And then this classifier is used to predict these behaviors on new videos, new unseen videos. And the tracking networks gives us the amount of time the mouse spends in different parts of the open field. Before we can take these features and predict the frailty, we want to adjust the frailty, which is denoted by Y here, for these covariates. So X denotes the fixed effects, and Z denotes the random effects. We treated age, sex, and weight as fixed effects, and diet and batches as random effects. The betas and the U's are the unknowns, and we estimated them from the linear mixed model, and we adjusted the frailty index for these particular effects. Then we use the adjusted, the slight abuse of notation here, but we use adjusted frailty indices, and model them, these test for adjusted frailty indices with video-generated features as inputs to the model, using both linear, non-linear, parametric, and non-parametric models. We regularized our models to penalize the multicollinearity in our inputs. We split the data randomly into two parts, training 90% and testing and tests at 10%. And as you'll see, we'll compare the models in terms of mean absolute error, root mean square error, and R square. So today I'll be showing results obtained using tenfold cross-validation for model selection on training data, although we can go ahead and tune the model on the entire training data and evaluate it on the test set. So although we are interested in predicting the biological age from the video features, we can also predict other things like chronological age, which serves as an empirical ground truth and also has a strong relationship to frailty. So we predict age, the chronological age using video features, and we call it the V-Fright clock. This is motivated from a paper that used manual frailty items to predict the chronological age. And they refer to it as a Fright clock. It stands for Frailty Inferred Geriatric Health Timeline. Next we address the main goal of predicting the biological age or the frailty index from the video features. And we test the performance of these metrics, of these features in predicting these different items on B6, DO, and combined B6 and DO data sets on the next few slides. The question we asked here is how accurately we can predict age from video features. So this is a figure from a previous paper where we can where we see that the video features can predict chronological age better than the manual frailty items. Not only that, the performance is more consistent and less variable. So we're trying to predict the chronological age from the video features. And we can see, we can see that our V-Fright model can accurately predict age with a mean absolute error of 11.8 on B6 data, and roughly with 70.6 weeks on the DO data and 15.7 weeks on the combined data. So here, next, we wanted to see which variables are important for determining, for predicting age in our model. So one way to do that is to look at the variable importance of the features. And we did this by shuffling the feature values and fitting the model using the separate features. And the model accuracies are greatly affected when the feature is important. Next, we tried to predict the frailty index from video features. So this part, and we call this the VFI. We knew before we began this that this would be challenging since we're dealing with a more genetically diverse population of mice. But we can see that, and although we can see that there's a slight increase in the error going from B6 to DO, but we're still doing quite well. For example, a way to interpret these errors is that, so an error of 1.2 means that one FI item is being misscored, or maybe two FI items are being misscored by 0.5 points. Similarly here, an item is being misscored by three FI items are being misscored by 0.5 points. So here are the errors. Based on the variable, again, we wanted to know which features help us make these predictions, which features are important, basically. Finally, we would like to predict the fraction of life lived from video features. We define the fraction of life lived as follows, where the fraction of life lived is constrained to lie between 0 and 1. So because of this constraint, we modeled the outcome, the random variable using a beta distribution. So these are very preliminary results. So given a video, we can predict when a mouse is going to die with 8% error on average. And so this is only for the DO data. We didn't do this for the B6 data since we did not record the age of death. So if a mouse lives up to 240 weeks, then we can predict when it's going to die with an error of about 20 weeks, is what these errors are saying. And finally, so we use advances in computer vision and statistical learning fields to extract features from videos of mice. We can predict frailty using video features with quite success in genetically diverse mice. We can further additional feature, like incorporate additional features to further improve our models and reduce these errors. In the future step, we want to extend our models to predict other things besides the ones we have predicted. And additionally, although we record only for 1 hour, these things can be extended to 4-day long-term assays, where we hypothesize that features of social interaction mice will change in frailty-dependent manner. Yeah, so thank you.